Ooh, so I'm looking at your backs today.
I got
Do
it.
you guys know how to switch that?
Yeah.
Okay.
There.
All right. So what's coming up? We've got I gotta switch some stuff here. Today we should be able to finish. Tomorrow we're going to review for the test.
Oh, nice.
You did not bring enough for everybody. You cannot eat Jiffy and crackers here. Sam, isn't that true?
I mean, that's what my understanding was.
Yeah, because he brought enough tuna for everybody.
Ew. Yeah, that was gross.
Well, it wasn't open. All right. No, anyway, and then tomorrow we're going to review for the test. Monday we're going to take the last test. Now, over the course of both of those days, we will have extra time. So what I would suggest you do is bring your computer tomorrow so that you can work on your homework during class, and then I can answer questions for you. Okay?
Are we going to review for the test like most of the class period tomorrow?
Yes.
Okay, good.
Thank God. To make or break at this point.
Sally Downer, we call her. The nice thing is, I think test 4 is easiest or second easiest. I'm not sure which. Now, test 1 seemed hard at the time because you didn't know a lot of stuff. If you were to take test 1 now, you'd probably say, oh, this is easy peasy stuff. All right. Today, we are on the percentile rank formula on page 357. And what it's talking about is we need to find out, well, what is your test score going to be? I brought a thing to help us talk about this whole procedure. I'm going to show you guys in Menominee so that you can see what we're talking about here. So I've got this thing here. If you notice, it's a bunch of wood like glued together. So when you see it, you will now understand what I'm talking about as I go through this. Okay, let's pretend. These are the boards for a wood floor. Okay, I've just shrunk down. So we would say these boards have a normal distribution. Normal doesn't mean as opposed to odd. Normal means it follows certain rules. Okay, and the rules are the mean, median, and mode are all the same number. That number is halfway between all of the other values. That distribution has about 68% of them between these two spots right here. 98% between these two spots here, okay? Now, I can't go 99% because I would need about 3 times as many boards. This took me a week. So 3 times as many boards would take me 3 weeks. Okay, this is called normal distribution. There are other kinds of distributions that are possible for those boards in a floor, a wood floor. The most likely one is random. What does random mean? Well, random means each length has an equal chance of happening. So how would that look? Well, if you looked at it from the end, it would be level like this way, right? Because each board would have an equal chance of being selected. And one other type of distribution is called uniform distribution. That is, all of the boards are the exact same length. Have you ever seen a wood floor like that, where they have, like, they'll make a parquet pattern or, what's that weave thing that they got going? Okay, so those are the different kinds of distributions that are possible. Now, in this case, we can figure out what the percentile is for any length. Now, this board right here that I just put up there is a certain length, right? And we can figure out what that length is. It looks to be about this height right here. So we would say its percentile, in other words, the boards that it is taller than, are these over here. Okay? And of course, it's shorter than these boards over here. Got it? Now let's translate this. And let's say this is people's ACT scores. Okay? People's ACT scores, or is it SAT? I forgot now. SAT?
No, we take the ACT.
It's ACT. Which one is it?
ACT.
It does say ACT, huh? No, it says SAT on page 357. SAT in 2014. So what they're saying is all the folks in the whole United States could be modeled by this function. Obviously, there are more than these many people, okay? So it would be a whole lot more boards, right? You would, because each one of these represents one board, so each person would be like just huge, okay? What would this height represent? The highest score, and this would represent the lowest score. So if we looked at it this way, this would be the number of people, right? The number of people that got the average score. What does it say is the average score of the people who took this test? Well, you can see it in the formula. $513. X is this, the length of any board. Can it do all the boards have to be this length? Heck no. I could get a different X, right? I could get this board here. Now these two happen to be pretty close to the same length, but I could get any board length at all. Question number 1 is, this is the shortest normal board I made. Does that mean boards can't get any shorter than that? Heck no, a board can be like this long, right? What is the one thing that isn't true? The boards can't be any shorter than 0, and they can't be any longer than, well, in the SAT, there is a maximum score you can get. Now, on boards, there is no maximum amount. Now, there's less and less chance the farther you go in this direction, right? Right now, the chance that the Packers have of winning the Super Bowl, 1 in 320. So in the words of Jim Carrey, or who was it that said, "So you're saying I got a chance?" I forget what movie.
Dumb and Dumber.
Dumb and Dumber. Yeah. So you're saying I got a chance. Okay. Anyway, you get the picture. Okay. 513 is right here in the middle. Okay. This is one way to do this data. The other way to do this data is the way that we're going to, the one that they have there, where it's not the picture of like how many people there are, it's the chance of having that particular score. So let's take out our graphing device and let's enter this formula into our graphing device. Dev's most. Okay. Jessica, I finished it, by the way. 1.
Oh, okay.
So if you want to do it today after class?
Yes.
Okay. Oops. All right. So here is my graph of that formula. Now, let's set the window correctly. Our x, what are our possible scores? Well, you can't get a score lower than 0, so I'm going to say from -1 just so that I can see the axis. And it's our score, highest score possible is around 1,500, but the chance of getting that 1,500 is pretty small. Our y's, okay, so we're talking about percentile. What's the lowest percentile you can get? 0. So if I say -1, we will see the axis. And what's the highest percentile you can get? 100, right? Okay. I'm going to make it 101 just so that we can see. Maybe I'll make it 110 just so that we can see the top of my graph. Okay, everybody have that entered on their graph. Now, so this is our formula. This is the graph of all of those different x's. Now, I'm going to scroll up here so that we can see our formula again. This is the graph of all those different x's. So if you had a score, if you were in the first percentile, you'd be down here somewhere in the 200 range, well, less than 200 range, right? By the time you get to a score of 200, you're already like maybe even 2 or 3 percentile, right? You'd be at the 10th percentile, right around, what is that, 350? Okay. The 20th percentile, if you had a score a little over 400. The 30th percentile, a score of a little over 450. Question: what do we know is true about a percentile of 50? You would have an average score, and the average score is x minus 513. Let's see why that is. So let's go to the formula, and let's say that we have a score of 513. If we have a score of 513, what does this part here become? 0. What is 0 times any number?
0.
What is any number to the 0th power? 1. What is 1 plus 1? What is 100 divided by 2? You see how that worked? Okay? Everybody good with that?
Yeah.
All right. Now, let's say that we had a score of 0. So let's, on our graphing calculator, figure out what our percentile would be. So we would take, according to our formula, 100 divided by 1 plus, I forgot to put in parentheses. Parentheses 1 plus second function e to the negative 0.01418 parentheses, or times, parentheses, 0, minus 513, close parentheses, and then close the other parentheses, and we see a score of 0 puts you at 0.069. Well, you would expect you to be, like if you have a 0, you would be, have a percentile of 0. But the thing you have to understand about normal distribution is that they have to account for the possibility of the impossible. Okay? There is a chance of anything happening. All right? So that's why it's not going to be exactly 0. But 0.069, that's pretty low, right? Out of 100. Okay? So if you look at the map, what must be happening here? 100, to get this low, what must this number be getting closer and closer to in the denominator? If this gets closer to 0, how do you get 100 things to be equal to 0? I have 100 pizzas. How am I going to make sure everybody gets nothing? I'm going to need to have a bunch of people, right? So that denominator must be getting very, very close to infinity. Well, it's not the 1 that's getting us close to infinity, right? It must be the e to the. Well, let's do that e to the business and see what we get. Would you agree? This part here would be e to the negative 0.01418 times negative 513, correct? So if on our calculator we pressed 0.01418 times 513, we get 7.27. Okay, now what does that mean? Well, first of all, why did I not put in the negatives on here? Everybody agree a negative times a negative is a positive, okay? So we would have e, so if we do second function e to that number, we get 1,443. I thought I just said it had to get close to infinity, right? Okay? In other words, $100 divided by 1443 must be 0.06. Actually, 1444. Don't forget the 1 that we add into this, right? 100 divided by 1444 must be 0.069. Okay? We're going to explore where that 1443 comes from. Okay? Let's do it this way. 1443 minus 513. Let's say if this person down here, if this person down here is in the 0th percentile, this person up here is in the 100th percentile, those two people are exactly the same distance away from 0. So if this person here has a score of 0, this person here must have a score of 1443 because they're equal distance away from the middle. 513. Okay, so this distance must be up to 1443, and this distance down here must be to 0. Not distance in scores, but distance in number of people. Okay? Go back to this. It doesn't mean this board and this board are exactly the same length from 0. It means they're exactly the same number of people from 0. Okay, everybody agree with that? Okay, here we go. So if we do the math there and assume that the highest score is 1443, and we did the math, well, 1443 minus 513 puts us at 930. So 930 times negative 0.01418 gives us 13.18 negative. Okay? Page 358, part A. If you look at this graph, what would an average score be? So I'm going to make y equal to 50. If y is 50, I'm going to make it a different color. I'm going to make it purple. If y is 50, what is an average score? What does it say? 513. Suppose that an engineering department at a university wants to admit any student who scores in the top 5% on the math portion. Okay? So we're going to find out what kind of score would you need to get into that school. Well, we take 95. All right? So here is 95. What does it say that score needs to be? 720 will be almost 95%. 721 will be for sure you will get into the 95%. How do we know that this business right here is a logistic function? Because that's one of our shapes of graphs. Notes. Now you might have this page already, but just in case you don't, let's make one more page worth of notes. Oh, come on. Okay. Let's go through the different shapes that we have for the different kinds of functions that we know. And it's going to take 2 pages to get all of these different shapes in, okay? So here you go. Let's start. So we're going to divide each page into 6 sections for our notes. And if you notice, I turned my paper sideways. Okay? So we've got 6 sections on 2 different pages. What's the matter, Eric?
Nothing.
Were you smiling because Madeline was
The side.
the sigh of, oh my gosh, Kevin, teach me something. Ah, here we go. First one, periodic. Let's review the periodic function that we were talking about that one day. Anybody remember it?
No.
Had to do with Boston? Close. The amount of daylight in Boston, okay? What makes it periodic? Well, each whatever, you come to the same spot that you were a year earlier, okay? Our daughter has PMS, and so each month she feels the exact same way that she felt the previous month, okay? Periodically. Got it? Now, characteristics of a periodic function. Sometimes it's going up. Sometimes it's going down. Everybody agree? Okay? Next one. Linear function. Now, the linear function that you see on this picture came from that one day that we were talking about. 2 animals.
Foxes or rabbits.
Got it? And the foxes were on the increase, and the rabbits were on the decrease. Characteristics of a linear function. Not only is it always going up or always going down, right? It's either one or the other. But it's always going up or down at the exact same rate, or as you said, slope. Linear. Third, quadratic function. Now, the quadratic function that you see pictured here is the one where you were throwing a rock off a cliff. Okay. Now, Jessica, I just finished the test, and one of the things you have to be able to do is to graph how a graph shifts based on whether it's an X shift, an input shift, or an output shift. So you see 2 graphs here. What kind of a shift is this for this quadratic function of throwing the rock off the... The only thing that's different is it's moving left and right. Which kind of shift is that? It's changing the which?
Horizontal.
Which is called the input, okay? How much did it change it? Well, it looks like it changed it about -1, right? It moved it back 1. How would you find that value out? Well, you would just substitute in a number 1 bigger than the one that they gave you. So if they said x is 1, you would substitute in 2, right? And figure out where you are. So that by the time this black rock was dropped, the blue rock had already fallen a certain number of feet. 16, actually. Got it?
Got it.
That's a quadratic function. Characteristics of a quadratic function. It's always, now be careful, not increasing or decreasing, right? Because half the time it's increasing and half the time it's decreasing. But it's always something. We were at the board that one day, and we were talking about the 2 people digging the garden.
Oh, I hate that.
I hate that kind. Can you give us a sigh, Madeline? Okay, thank you. All right. But what was always happening? The amount that it was changing was always the same. Not the amount of the change, but the amount that the change was changing. It was always either 2 or 3 or 4. What's happening here? Well, if you notice, what's happening is that each second, it's increasing its distance, right? And the amount that it's changing is 9.8, slower than it was going, faster downward than it was going before.
Was
Yeah.
that the one with like the difference 1, difference 2, or whatever it was?
Right. We call what we're talking about that's constant the second difference. Does anybody want to review that just to put a little table on that table? So let's make a little addendum to that question right there so that you can put a table onto that graph, onto that section of the graph. Okay, so let's say that we have x, f of x, and I'm going to use f quote x and then f double quote x because that's what we're going to be using in calculus. Okay, give me a number that the second differences are always going to be. Don't say 2. Okay, 3. All right? Give me a number that the first difference is. And it can be anything.
105.
That will make our math a little bit difficult as we get farther over, but let's say this number is 1. I know I did. 105. We know that number is what compared to the previous number? Three bigger. So what must have this been? What? Right? 3 bigger. So what's this next number going to be? And the next number. And the next number. Okay. Now we're going to go back one more step. We know these two numbers are going to be 102 apart. So give me this number here. Did you say 50? That's an easy one to do. 50 is 102 bigger than what? Negative 52, right? What's 100? Okay, so now how far apart are these two numbers going to be? 105. So what's this next number here going to be? Right? 50 plus 105 is 155. How about the next one? What's that going to be? You see why the numbers that Madeline gave us are not the easiest numbers to work with, but we can do it. Right? What's the next one? 74. And then the next one would be 488. Right? And then our x can actually be any number because we're only talking about how it is compared to f of x. We don't have to say how it is compared to x. So in other words, this graph we know goes like this. We don't care whether it's moved this way or moved this way. We know that at its peak, we're past the peak because our value is greater than 3, or is 3, and so we're way past the peak. It's getting much bigger. How long ago did we pass the peak? Well, what is 102 divided by 3? 34? So we were at the peak back here at negative 34. Because this is 34 iterations later, we're at 102. You keep on subtracting 3 each time. 34 times ago, you would have been at 0. Okay, next. The next function is the cubic function. How can you the one that we did was the making that drug, if you recall, and we were doing how much the batch size was compared to how much the drug cost to make.
That was horrible. I really hated that lesson.
Can you give us a nice sigh to show you how much you hated it?
I don't know if I have enough size in me anymore, Kevin.
Okay. Well, anyway, you get the picture. A cubic function is always increasing or always decreasing, right? Next one, we didn't do much with absolute value functions, and frankly, it's because absolute value functions aren't, they're kind of specialized. Square root function. The one that we did is the distance versus time back in 11E, don't remember what it was. But the square root function, we had to make an exception. Because if we would have drawn the whole quadratic, what would have happened after this point here? We'd have gone downward, right? Like this. If that would have happened, what test would have we failed? Don't say test 4. The vertical line test, right? Okay, you got all those. Page, or next page. Let's go through those functions. The first one that we talked about was the inverse function. And the one that we did for the inverse function was a gas under pressure, right? No matter how much volume the gas has, it would still have pressure. No matter how much pressure the gas is under, it still has some volume. The other one that we did later on was that beam or support column that we were making. No matter how much, how big the column is, it's still going to have some shear force on it. And no matter how small that column is, it will still be able to have some force on it. So the inverse function is always increasing or always decreasing. And the other thing that's true is it always has two asymptotes, a vertical asymptote, and a horizontal asymptote. Polynomial function. We also call the polynomial functions power functions. If you recall, this was our roller coaster problem, right? And we gave a polynomial for it. And there was a test question that we had on this one. The test question was, how many turning points does this graph have? 1, 2, 3. But the test question was, what power is this polynomial? 4. Good. It's supporting. How do you know it's supporting? Because the power is always at least as big as the number of turning points that you have. Okay. The next two are both exponential. What is the difference between an exponential and an inverse? An exponential only has one asymptote. Okay? In this case, it's just going to keep on getting bigger and bigger no matter how far backwards you go in time. But it's never going to go below, in this case, 0. Exponential growth, no matter how far back in time you go, it's not going to get below 0. But as you go forward, it's going to keep on getting bigger and bigger forever and ever. Now, on those decay and growth graphs, we need to do one more thing. Decay was e to the negative something, or 0.5 to the t. Growth is e to the positive something, or what to the t? A number bigger than 1 to the t, right? So you can tell by looking at the formula whether it's going to be decay or growth. Okay. Let's go back here. The next one was the surge function. If you recall, the surge function was where we had that drug that we were trying to make sure it was effective within 20 minutes. Or no, 0.2 hours, 12 minutes. And it was effective for at least 3 hours, right? And it couldn't go over 4, but it wasn't effective until it got above 2. So the surge function started out kind of like a quadratic, and it ended out on the right side kind of like an exponential. So it was two functions with the variable in two different unique spots. Right? One of the spots was in the exponent. The other spot was in the coefficient out front. And then the last one we had was the logistic function, and the one that they gave us was penguins, right? The least number of penguins, and then the most number of penguins, that was the carrying capacity, or the K value of the function. And P0 was the number of penguins at the beginning, right? Now, the one that we're doing right now is most like, you look at the graph that you made for the SAT scores. It's a logistic function. Okay? Now, we would say the maximum percentile would be like the carrying capacity. Okay? One of the things that you notice is that this one has a value where it crosses the x-axis at 0. You could have it cross at any point in time. Like, for instance, right now, they're talking about, what animal is it that they said that they're almost dead? Oh, killer whales. Anybody hear the story about killer whales in Washington? Why are the killer whales dying in Washington? Because their main food source is Chinook salmon, the biggest salmon there are. And Chinook salmon population is decreasing because they breed in rivers, and they dam the rivers, not like go to hell. They put a barrier on said river. Let's hear a sigh for that one. Bad joke, Kevin. Okay, thank you. All right. So anyway, they dam the rivers, and so not as many Chinook salmon are being growing, and so the killer whales don't have as much food source, and so killer whale population is decreasing. So in that case, we might be at, say, this point right here. We have two choices that could happen right now. One of them is Chinook salmon could decrease. How would that happen? Well, pretty easily. We can take this graph and switch it around the other direction. I think this is the sign that I would switch. Nope, that's not the sign that we would switch. This sign, let's try this one. Nope, that's not the sign we would switch. Oh, did I erase the right number? No, I erased the decimal point. I gotta erase the number. There we go. So if we would have had a positive 0.1, in other words, our population is decreasing by 0.1, carrying capacity wise. And we're at this point right here. What just happened to the chance of the killer whales rebounding? It's going to go down exponentially. Now I have a hunch what's going to eventually happen is it's going to reach 0, right? I wish I would have been alive back in the days of the passenger pigeons. Has anybody ever heard that story about the passenger pigeons? Back in the 1800s, there were millions and millions of passenger pigeons. They said the sky was dark when the passenger pigeons flew over. 1914, the last passenger pigeon died in a Cleveland zoo. I do not understand how that happened. They said it was because people were killing them. I can't buy that it was hunters that killed all of them. I know for a fact hunters are incredibly inefficient at killing everything. Right? Have you been able to kill every animal that you shot at? Have you been able to see every animal that was there? Have you been able to shoot every time you saw one? I mean, the chances of killing with a gun something, I mean, people say it's really easy. Those people are not hunters. All right? I was watching a fishing show the other day, and they had this camera, and this guy was fishing for perch with a camera, and he was showing that the perch would bite on his little minnow head, and then he would reel it in. Okay, here's what I know for a fact: fishing is not easy. Right? I've been there. Anybody that says, "Oh yeah, that's so easy." So I don't know. I don't know what happened to the passenger pigeons, and I don't know what's going to happen to those killer whales. But here's the situation that we're faced with here with this problem. Page 358 says, another example of a logistic function. So let's look at this next logistic function problem where it says we're going to start with 15,000 students at a residential college. 5 students return from spring break infected with a virus causing zombieism. A week later, 50 students are infected. Assume that N of T, the number of students affected with the virus, can be modeled by this function. So we write 15,000 15,000 over 1 plus b e to the negative rt, where t is the number of days since the students returned from spring break, and b and r are constants. Okay, so let's make a table here where we have time and number at that time. Okay, it says that at time 0, 5 students were infected. At time 7, so time is going to be in days. At day 7, 50 students were infected. One of the things that you have to do for test 1, Jessica, is you have to be able to find the ratio of those two values. How do you find that ratio in this case? Would you agree it's 50 divided by 5 is 10? It's the ratio of the new divided by the old. Okay, so let's go through the math of this first one right here. So the math says that we would have 5. That is 1,500, or 15,000, excuse me, divided by 1 plus B, which we don't know what that is yet. But we do know this. E is going to be to the 0th power. Why? Because if t is 0, it doesn't matter what r is. So our goal is to do the math to get t all alone. Well, in this case, it's pretty easy because if this is 1, right, then all we have left to solve for is b. How do we get b all alone? First step. Take 15,000 divided by 1 plus b and multiply it by 1 plus b so that those two cancel. But we have to do the same thing on the other side. 5 times 1 plus b, which is 5 plus 5b, will equal 15,000, correct? Or 15,000 minus 5 is 14,995. So we're going to subtract 5 from each side, and then we're going to divide by 5, and we get so B is 29.99. So 10 days later, or I'm sorry, it's 7 days later, isn't it? 7 days later, we have 50 people that have the disease, and we know that's going to be 15,000 over 1 plus. We just figured out that B is 29.99. And E is going to be to the negative 7 times R. Why 7? Because it's 7 days is 50 patients. 7 days is 50 patients. Now, if you notice, we have a 1 variable to get all alone. We need to solve algebra to get that 1 variable all alone. First thing we can do is take care of the multiplications and divisions. We're going to multiply both sides by 1 plus 299 e to the negative 7r. And we get 50 times 1 plus 299 e to the negative 7r. That's going to equal, well, if you notice on the other side, these are going to cancel. So it's going to be equal to 15,000. Next math. See if the person sitting next to you knows what you can do next. What are you dividing by, Eric?
Not dividing yet.
We can divide both sides by 50. And what will we have? 1 plus 2999 e to the negative 7r will equal how much? Is it 300 or 3,000? 300. Next, subtract 1 from each side, and we have 2999 e to the negative 7r is 299. Remember, we're still trying to get r all alone. What should we do to both sides? Divide by 2999. And all we have left on the right side is e to the negative 7r. And on the left side, we will have 299 over 2999. When you get to this step right here, use the log exponent equivalent form. Remember what that said? It said if you take, in this case, the base is e, so we can take ln, because ln has a base e. Oh, 299 over 2999, that will equal negative 7r, because a log is an exponent. This is an exponent. This is an exponent. We have one more thing we can do to both sides. Divide by negative 7, right? And we will have r. So on our calculator, we can press ln of 299 divided by 299, divide that by negative 7. It will tell us that our ratio is 32. So about 32% of it's a 32% per day increase, or is that 33? About a 33% per day increase in the number of people that get this disease, zombieism. Avoid the zombies. I wonder why it was a university, because I would think zombies would be more common like at bars than at universities. I don't know. Okay. How many students will be infected after 3 weeks? So we're looking for a number at 21. Why 21? 3 weeks, right? Is 15,000 over 1 plus 2999 e. Where'd my b go? Oh, I forgot the b. Yeah, we got 2999 e to the negative 7 times 21. So 15,000 divided by parentheses 1 plus 2999 times e to the negative 7 times 21. So we will have, everybody will have the disease in 3 weeks, unless I made a mistake there. Okay. Page. Oh, break time.
I was just gonna ask you. I kept hoping that you would like cover some of it.
Yeah, especially like when we got to the back of this.
I filled in as much as I could for the back.
else was in the book except for expulsion. But at least when I typed in the search, I couldn't find it. As much as I would love to actually read the chapter. Yeah. I've made it this far. Actually, that's not true. I did for like the first 3 days. Oh,
Yeah, it's very dry.
dry, useless. So, I don't know. If it wasn't so, I don't know, the textbook I have for econ, it's hard to read because I don't really understand economics in general.
Yeah.
But it gets to the point and then gives you the world and then moves on. I don't know. I feel like it's pretty good. I still don't enjoy reading textbook because I have. At least I don't feel like it's a waste of my time to actually read the chapter.
I was super sick.
I did that for American.
I don't know why. I was like,
Chapter
so I was like, yeah,
the quiz.
it's kind of weird.
Nothing. Nothing in the
Now
quiz.
when I was in something
Anything in the
really-
chapter. I was like, oh,
But yeah,
like the past 3 American government quizzes I took. Didn't read it.
I don't work
100% on each one.
Wow.
Nice
Nice job.
My brother's birthday.
At least
You don't work that day too? Yeah, I worked 26 hours this week. I told her that the schedule this month.
All right. 27C. It tells us that each day, or each... Would you imagine that earthquakes of high magnitude on the Richter scale are more or less common than earthquakes of a low magnitude? Well, there was an earthquake this morning in central Tennessee that registered 4.4 on the Richter scale. That's almost nothing, she says. And she's actually pretty right. It's a pretty small earthquake. In fact, it was felt as far away as Atlanta. The thing that I always think is funny is, have you noticed that? Oh, you guys probably don't watch the news. But I've noticed on the news that they'll say things like, this storm is going to affect 40 million people. You don't watch the news, so you don't know that. Well, what do they mean? Well, I mean, it's going to rain. Okay? And 40 million people are going to have rain. Who cares? So they try to make it sound worse than it is. People felt this earthquake as far away as Atlanta, Georgia. Which, I mean, it's like a couple hundred miles. Who cares? Okay, it says here, what type of mathematical model might relate the frequency and the type of earthquake? Well, let's think about it. So if we had let's say this is the number of earthquakes and this is the magnitude. Okay? So we would say that if we had a magnitude 5 earthquake, okay, there might be a lot of them. Magnitude 6, not as many. Magnitude 7, not as many. Now the question is, are these going to be linear? I don't think so, because is it possible to have a magnitude 13 earthquake? Yeah, but there's probably only going to be one of them. Is it possible that there would be no earthquakes? Well, that doesn't make any sense, right? Actually, what it should be is it possible you had a magnitude 16 earthquake or 17 earthquake or 18 earthquake? Well, it's possible, but, you know, the Earth is eventually going to fall apart if they're going to have that much. Okay, it says there are an average of 16 earthquakes each year in the world whose magnitude is greater than 7. The Gutenberg-Richter law says that the log of the number of earthquakes is A minus the magnitude of those earthquakes? Well, in this case, it says that if n is 16, so we would say the log of 16, which is 1.204, that is equal to some number minus 7. What is that number, part A? .204, right? So that's our first parameter that we're going to consider. B, over 8,800 people died in the Nepal earthquake of April 2015. I had a friend who was studying in the United States that spring, and he said, I gotta go home. So he actually graduated from college early so that he could go back home to Nepal and help his family because it was just devastating there in Nepal. Okay, the earthquake had a magnitude of 7.8. What do we get if we take 8.204 minus 7.8? 0.404, right? So the log of n is going to be 0.404. Everybody agree we need to get n all alone. How are we going to do it? Well, do we have any additions and subtractions to take care of? No. Do we have any multiplications and divisions to take care of? No. The only thing left is logs and exponents. Let's page back in our notes to find that formula again. If you're talking about logs and exponents, it was just the other day. Here it is. Nope, there it isn't. Here it is. Nope, there it isn't. I know we did it one day. Here it is. No, that's not it. Where we had the log of a sum is the sum of the logs, log of a difference. Somebody have that page where I wrote multiplication, division, log laws. Yeah, I can't find that page in this book right now. I know up at the top I had written like page 245. No, I can't. Oh, I know why. This is the other class's notebook. Okay, that's why I don't have it. Somebody have their notes for that page just so that we can see them?
Yeah, right here. Got it. Just
Perfect.
In different colors too.
Can you share with us a psi just so that we can know where exactly we are? Okay, so we're down to this step right here where we're the equivalent step. And remember, a logarithm is an exponent. Okay? So we are going to change this log equation into an exponent equation. That's what we're going to do because we will then be able to solve it mathematically. Okay, so a logarithm is an exponent. So this is our exponent right here. To the 0.404. What is to the 0.404? It's 10. How do we know it's 10? Because if they don't give us a base, we assume the base is 10. How about if they write ln? We assume the base is e. So we're going to take 10 to the 0.404, and that's going to be n. 10 to the 0.404. So the number of earthquakes that are going to be that 7.8 is 2.53 earthquakes per year. Or about 2.5 earthquakes each year are going to have that magnitude. Next one. Earthquakes of a magnitude 4 to 4.9 are generally strong enough to be felt, but they usually do not cause serious damage. Approximately how many earthquakes in this range occur each year? So we have two log problems to solve. One of them is the log of n is a minus 4, and the other one is the log of n is a minus 4.9. What did we say our a was? $8.204. Find these two answers. Tell me what n is, and I'll help you. Go. You can use the math right above it there to figure out your answer.
So we could try and go over here.
Yeah, you could assume that the 10 is down there, but you don't need to put it in because you just assume it's always 10. So log of n equals, what's our a? 8.204 minus 4. What do you get if you take 8.204 minus 4? $4.204, right? So you would write 10 to the,
Just like right underneath it.
yep, just like I did there. You notice how I changed in the yellow, I changed log n equals 4.404. I changed it to 10 to the 0.404, but yours won't be 0.404, yours will be 4.204. 10 to the 4.204, and what'd you get for the number of earthquakes that is? $15,995. So the fact that 4.4 earthquake happened in Tennessee today looks like that happens about 500 times a day, right? 15,000 divided by 365.
Do we have to,
Then the range 50 times a day.
do we have to like round it up because of that or no?
I would just write it as 1596, 15,996. It's just close enough. What? What'd you get? Is it 50? 15,000 divided by 365. What do you get? Oh, you didn't.
No, I stopped.
You stopped what?
I have 10 to the 4.204 and 10 to the 3.304, and that's where I left off at.
Oh, because you didn't get out your calculator to figure out what it is.
Yeah.
Okay. And what did you get for the 10.304? it's 4.9. Yeah, 10 to the 3.304 is. So it's somewhere between 2,014 earthquakes of that magnitude a year and 15,000 earthquakes of that magnitude a year. Well, 2,000 would be 7 a day. 15,000 would be 50 a day. So are those earthquakes pretty common?
Yeah.
Yeah. So when, what's his name on the Today Show, the weather guy says, yeah, there was a 4.4 earthquake in Tennessee today, we could have said, well, dude, there's like 50 of them a day of that magnitude. Right? Somewhere between 7 and 50 of them a day. You don't need to give us the lowdown on that. Today's news. Somebody died today and somebody was born. Okay. Next. It says a minor earthquake of 3.3 releases the energy equivalent of 10 metric tons of TNT, roughly the equivalent of the Chernobyl nuclear power plant. More generally, the relationship between TNT equivalent, measured in metric tons, and the Richter magnitude, M. So if we take 1.5 times the magnitude, we will have the log of the amount of energy plus 4.82. Part A. What is the TNT equivalent of a magnitude 6.5? Let's do the math for a 6.5 earthquake. So we would take 1.5 times 6.5. That will equal whatever our energy is plus 4.82. What should we do first to solve this problem? What do you always do first? Additions and subtractions. In this case, what are we going to do? Subtract 4.82 from both sides. Good. So I'm going to take 1.5 times 6.5 and subtract 4.82. I'm going to get 4.93, which is the log of E. What's my next step? Yep, exponent to log. So we're going to switch exponents and logs around. Remember, a logarithm is an exponent. So the 4.93 is the to the. What is it? What's number is the base? 10. So it's equivalent to 85,113 metric tons. Or we would say 85,000 metric tons of TNT. Next one. If the magnitude is increased by 1, what factor does the energy increase by? Well, let's graph it. I think it's easier to see it on a graph. Let's see, this is 27C. So if we write it as 1.5, and then I'm going to use x for my variable, equals log of my y plus 4.82. And I should say my x's go from, let's say, 0 up to, even if we went 7, that's really a big earthquake, right? And then the metric tons, we should go from 0 up to, well, if you notice, we were at a 4.2 earthquake and it was already 40,000, so maybe we should go up to 1,000,000. 3, 4, 5, 6. That'll get us close, right? So if we're here at, well, let's take that 6.5, or no, 3.88 earthquake. Oops. Why is it way over there? Let's say X is 3.88. If it's a 3.88 earthquake, it's got 10 metric tons. If it's a 4.88, notice it's 316 metric tons, or about 300 times as much earthquake power. Because remember, we're taking 6.5, and if you do 6.5, 10 to the 6.5, or I'm sorry, 1.5. 10 to the 1.5, oops, clear. 10 to the 1.5. You notice it comes out to be about 31, oops, you can't see that, 31 times as much energy. Last one. Here's another situation which involves a logarithmic model. The manager of the city water department has determined that an experienced meter reader can read at most 70 meters each day. However, it takes a while before the meter reader can become this experienced. Assume that the number of days, t, until the meter reader can read n meters is modeled by the equation t, time is c times ln of 1 minus the number of meter readers divided by 70. And it says, after 1 week on the job, where it says C is in, T is in days. Okay, so after 7 days, he can read 40 meters. So we would say 7 equals C ln 1 minus 40 divided by 70 meters. We want to get the C all alone. Divide both sides. Divide both sides by our other stuff. ln of 1 minus 40 over 70. So on our calculator, ln 1 minus 40 divided by 70. Our constant is negative 0.847. So how many meters will he be able to read after 2 weeks? 14 is negative 0.847 times ln of 1 minus n over 70. We want to get the n all alone. Or, I think the easiest way is to just graph it. So let's put it into Desmos and figure it out. So, y equals negative 0.847 parentheses ln, I suppose we should do times, ln parentheses 1 minus x over 70. So you can see how the number of meters read each day is changing. Let's say we go up to 30 days. What am I doing wrong here?
I think your constant 0.84 instead of
What did I write?
or yes,
It's positive?
or no,
7.
I thought you said it was 8.4. Sorry.
Let's try it again. Seven divided by ln 1 minus 40 divided by 70 is, oh, it's negative 8.26. Where did I?
That's why I was kind of confused.
Negative 8.26. Okay, so let's put that into our formula. Negative 8.26. There we go. So it says after 14 days, how many meters is he reading? After 14 days, he's reading 1.83 meters. And then how long will it be till he can read 65 meters? Well, we have to make sure y goes up that high, right? Y goes up to 70, let's say. Well, we aren't close yet. Let's make x be 100. There we go. Bye. Looks like he's able to read 70 meters in about, or 65 meters in about 70 days. Last part. The log of x minus 1 plus the log of x plus 2 equals 1. Another equation, the log of x minus 1 times the log times x plus 1, x plus 2 equals 1. Why does it say these two numbers should be the same? Because adding logs is the same as multiplying numbers. So let's look at this one right here. Let's graph that equation. Oh, you guys, I'm sorry, I wasn't showing you that, was I? Let's graph that first equation. Log x minus 1 plus the log of x plus 2. And let's compare it to the log of x minus 1 times x plus 2. And if you notice, those two are the exact same, except for what happened when we added that second graph in. Did you see a phantom solution appeared? So, if we look at that first graph, it says use the graph to solve that equation where that equals 1. So if we put if we put y equals 1, we find our solution to be at the point over 3 up 1. If we take 3 minus 1 and we take 3 plus 2, we get the answer 1. Then it says, what happens if we have the product equation? Notice it says the answer is -4. So when we have a product, when you get this squared problem, you end up with an extraneous solution, or a solution that isn't part of what you're going to be talking about. Because of that, you need to recognize when you solve a log equation, you can end up with an extraneous solution. The easiest way to prevent it is to graph it and then solve the equation that you get appropriately. Section 27.D is not on the test. There are only applications for Section 27 on the test. Okay, tomorrow we are doing the review. Now, Lauren said, how long do we have that you can review? You can review the whole hour. Bring your computers tomorrow and bring your... and then so that you can work on your homework after the review is done. All right. We are done 15... Oh, I got a take attendance. Forgot to do that. We are done 15 minutes early today. I would love it if you would, during the time that remains, work on your stinking homework. Now, I said that because... there. Okay. I got it out of my system. I'm good now. So work on your homework. Get that done. Everybody's got stuff to do. So we're going to review tomorrow and finish our homework. Test is going to be on Monday. This weekend, I have a hunch your other classes are going to be done, correct? You don't have your other classes on Monday? So you'll have all the time in the world to study this weekend and get your algebra done so that we can do well on test 4. Yeah.
Just in regards to the math lab.
Yeah.
Did we For some reason, I was under the impression that we didn't have to do lessons 1 and 2.
1 and 2?
1 and 2. I don't know if that was something we. Is that we're supposed
You didn't have to do them that week, maybe. I don't recall ever saying you don't have to do them,
Okay,
but
and I don't know why I was under that impression. I just wanted to clarify.
yeah, I don't remember saying that, but I am definitely not saying I would have never said that because
Okay.
way weirder things than don't do lessons 1 and 2 have come out of my mouth.
Okay.
All right.
If we are like behind like 53 assignments, like how bad would that affect your grade?
I'm going to talk about that in just a second. Nick, Michael, absent.
I'm here.
Marlena. Oh, you are here. Sorry. Marlena, absent. Gavin's here. Janae's absent. Felicia's absent. Nicole's absent. Eric's absent. Phil is present. Grant is absent. Connor is present. Eric is present. Laura's absent. Madeline's present. Jessica's present. Lauren's present. And Sam's present. Okay. If you guys want to get to work on your homework, you can. I'm going to talk to Madeline for just a minute and explain what she's asking about. So suppose here is the pie of your grade. Okay? It's divided into 10% of that pie is in class. 30% of that pie is homework, my math lab, and the rest is tests, which makes the tests worth 60%. Got it? Okay, so here's what Madeline is wondering. Suppose of the 88 lessons, I have 53 that I haven't done. So let's say she's done that much. Okay? She wants to know, what is her grade going to be? Well, there is a part in the syllabus that says there is a different way than you can get the grade than your everything. You can get the grade based on your test. So what fraction of the tests is shaded? 100%. So what grade would you have? A plus, right?
Yeah, but I'm not that smart.
Okay, so let's say that instead of 100%, let's say that instead of 100% of the pie, let's say you only had 50% of the pie shaded. So your grades on the test part would be 50%, which is an F. Well, let's shade that exact same half the tests over here. Well, half of 60% is 30%, right? You said you had 30 out of 88 left to do here. Okay, so you've done about a third of them, right? But there's 30%. So a third of 30% is, let's say this is 10%. Okay? And let's say you showed up every single day. Okay? So that you get 10% here. Would you agree you still have 50%? 10, 10, and 30 is 50%? Now, if you were to change this so that you did all of those, that would make this section here not worth 10%, but 3 times that, or 30%. 30 plus 40 plus 30 is 70%. And what is a 70%? It's a C. So, it depends. It depends. If you suck at tests, do all your My Math Lab, and show up for class. Okay? If you are great at tests, you don't have to come to class. You don't have to do your homework. You just have to get 100 on every test. What characteristics does that person have? They probably already knew it. I mean, I can't imagine how you would get 100% on every test unless you knew what the questions were and you knew what the answers were or something before you took it. Right?
Is that a possibility?
Is it a possibility? So anyway, that doesn't totally answer your question, because if you have 53 My Math Labs to do, you either are in good shape or bad shape.
Bad.
If you know what you're doing, you're in good shape. If you don't do well on tests, you're in bad shape. If you're somewhere between those two, you're between those two. Got it? Yeah, Jess.
So
I can print it off for you right now.
just doing the homework you get credit for it, or do you have to get it right too?
You only get the points for it if you get them right. It doesn't say, oh, it is so cool that you did your homework. I'm going to give you a gold star. I don't have it set up that way. I suppose I could. I just don't. Okay, get her done. If you don't have a computer here, you can work in the computer lab downstairs in the library.
Hey Kevin,
Yeah.
are you actually gonna go through the review like with us tomorrow, or are you just
You guys are going to work. I will answer every question that you ask me tomorrow.
So every question on the review that's
Only if you ask me them. I am not going to say, here's how to do question 1.
so basically?
And the reason for that is, we already know what happens if you get the helps on the show me how to solve this and give me an example. We already know what happens when you get to the test and that's all you've done.
Lee. So Kevin, that took you a week to make?
Which thing? That thing? Yeah, it was a week. I can show you pictures. I've got pictures of the production. Oh, let's see here. My pictures.
Oh wow. Actually in the library.
Measurement?
Yes.
Good. Great.
Right, a whole tour with
Oh, wow.
a-
It's on the printer there, Jess. Oops, those are all the pictures.
That looks like a lot of work, Kevin.
It was.
Looks like
But you are worth it.
It's like almost about as much. That's probably more work than what I put in this class.
But you got to remember that I've used it for other classes.
Yeah.
So multiply that by say 100 students. So 100th of the amount of time that I put into it so far, you are benefiting from. So if I use it again next year, then it'll be 200, let's say.
So when I fail this class, I'll see it again.
You will see it again. When you fail this class, it will be a cold day in some faraway spot because you are not going to fail.
Okay, Kevin.
You aren't even close to failing. I don't know why you think you are.
No, she's never came into simple at all or anything like that. Most of the time when we give her a reply, it's just short, couple sentences.
Yep. Have a good one.
Yeah, the best thing about that.
You can wander down to the table because I think there's a class in here. And then I have to stop by my classroom to drop off the normal curb distribution thing. And then I'll come down the back stairs, so I probably won't see you before I get down there.
Okay, so
Just that table, yeah.
okay. Then I can just leave it there if I'm done before you get back.
Oh, I will just be, you will get there like a minute before I will. Yeah.